Okay, everyone, let's start our first class for mechanics of materials. Since a lot of reasons, so we have to use the distance learning for our first classes. But I think we should learn how to. First, we should learn what is the mechanical mechanics. In your first year, I think the mechanical, uh, you have learned the statics and the dynamics. And what's difference between the mechanical of materials and the static or dynamics? First, you could see the load type. We have at least two major I could separate it in two major topic. One is the load types, and the two is the body types. The load types, the extensional load. The body type is rigid body or particles. Is that is means this subject. Maybe this subject have the external loads, but the deformation of its shape will not change. So the body type is rigid body uh, or the particle, no, or the particles. The particles means a small, like a small ball or something else. The rigid body is that body is very have a very large stiffness, so it won't easy to change or never change its deformation. So by those deformation, if you use those deformation to solve one problem, if this problem is statics, it means the summation of the external load, especially the external force, will equal to zero. And if a subject have the force, it also have the bending moment, right? Yeah. So if the force and the bending moment, the summation of the force and bending moment, all of those are equal to zero, that you solve one static problem. Statics problem. Yeah. So the static problems equal the summation of force and summation of moment equal to zero. And if you solve the problem is the dynamic problem, that means you have to satisfy the Newton's second law. The Newton's second law is uh, is very familiar with us. Since you're junior high school or senior high school, you have learned the summation force equal F equal to M mass mil plate is escalation. F equal ma. That is dynamics. The most easy equation in the Newton's second law. Yeah. So summation F equal to ma. The mass is the total systems mass, and A equal the systems escalation. And it also have to equal to the external bending moment equal to what the inertia, and the alpha is the angular escalation, right? Is That is from your dynamics. Your dynamics learn that the F equal to ma, and the summation bending moment equal to inertia mil plate, the escalation of angular velocity of angle. Yeah. Okay. And also, and what's different between the mechanical of material and the statics and the dynamics? That is similar. Okay. The load type, if you solve the mechanic of material problem, you have to consider first the extensional loads, extensional load, and the internal loads. That is, in the body, you not only have the extensional force or extensional moment, but you have to also consider what inside the body, the what force or the bending moment inside the body. That is very important. And the those force or bending moment or causes the body change its shape. Maybe the original shape is the rectangular, but after it changes its shape, maybe it's become parallel the parallel type, or it become a circular. That is possible. Rectangular becomes circular. Okay, so the body's deformation, the body's shape can be changed. So the body type is deformable body. Deformable body. Okay, so the internal load. So we have to consider for what the top the the subject we have to consider is the internal load intensity and the deformation. Uh, how much force or causes this body have the deformation, have the associated deformation, or how the bending moment or how the force will causes inside the body. So you have to consider the internal load intensity. Internal load intensity, that means the force causes the force inside the body. What acts inside the body? That is you have to consider. That is the difference between the it's the mechanics of material and between the static or dynamic. And here's come the introduction. We have to list the uh, in this symmetry. We have to learn some topics, and we will introduce it in the brief talk. Okay, in this page, the internal force intensive is related to what? Related to stress. Related to stress. Okay, in chapter 1, we have to teach you what is stress, what the unity, how to calculate what will causes inside the body, or how to calculate the stress, what force will causes which type stress in this body. Okay, and second, the force will causes the body have the deformation, so we have to calculate the internal deformations intensive. The deformations intensive is related to strength. Okay, the strength is in the chapter 2. Okay, then the chapter 1 stress and chapter 2 stress. That means the interaction. Okay, they have the interaction. So you have the stress, your causes the strength. You have the strength. Maybe some strength or causes the stress. So the stress and strain that they will interact each other. So the chapter 3 is the constitutive equation. The constitutive equation is told you the stress and the strength relation. Okay, the stress and stress relation. That is in chapter 3. And from chapter 4 to chapter 8, that is told you the extensional load. There is many type of load. Okay, there is axial force or shear force or bending moment or the torsional moment or the pressures. Okay, and those different force will let the body, okay, let some body have different deformation. Okay, let somebody have a different deformation. So how to calculate and those type or those extensional loads will how those extensional load will causes the stress or the strain in the body. That is we have to consider, we have to calculate. Okay, we will teach you in this subject. Okay, in the subject. Okay, the stress, there is two type of stress. One is called normal stress. One is called normal stress, and the other is called shear stress. Okay, the normal stress and the shear stress level, if we calculate it in a point, and there will have different solution. Not only one solution. If you if if you cut it in the different plant, okay, cut it off in the different plant, you cut stress, or you cut the horizontal or the vertical, or at this point you cut it horizontal or you cut vertical, you will get different normal and shear force. That's called the transformation of normal and shear force in chapter 9. Okay, chapter 9. And the strength also have the normal strength and shear strength. If a point you cut it in the vertical direction or the horizontal direction, you will get the different in the same point. I have to told you, in the same point you will have the different normal or shear strength by how you cut it. Okay, so the transformation, that's called the stress or strength transformation. That is the topic in chapter 2, chapter 9 and chapter 10. So it's called the stress transformation. Oh, okay, that is what I told you. In this point P, if you cut vertically or cut horizontally, that you will calculate different normal and shear strength. Okay, and stress also you have different normal. You will have different normal or shear stress if you measure it in the different directions. For example, there is some we have some method to measure the strength, or they are called the strain gauge. There is the 45 degree, or this called the list is 120 degrees. The strain gauge. In different strain gauge, you will measure the different strength. In different strain gauge, you will measure the different normal and shear strength, and they will told you, how to calculate the point strength is what, how to recognize in this point the stress and the strain, how to represent it. Okay, that is the topic in chapter 9 and chapter 10. So okay, let's start at the 1.2 sections. 1.2 sections. 1.2 section is very similar with the statics. Okay, the statics, the equivalent of a deformable body. Okay, equivalent of a deformable body. That in statics, that is the equivalent equation. The equivalent equation means the body won't have the deformation, so it's undeformable body. Okay, and how should we calculate the deformable body, the equivalent of deformable body? First of all, we have the surface force. Okay, just like statics, we have the external force. The external force, you have several several type of the force type. One is the surface force. The force act on the body as in an area. So that is a surface force. And if the body have its weight, so we have the body force. Okay, the body force usually W equal to mg. Yeah, as you know. Or if it have the escalation, the body force, maybe you should write it equal to F equal to ma. Yeah. Okay, so at one point, if you you concentration it in the in the mass, in the max position, in the body's mass position. That is the concentrate force. So usually the body force is the concentrate force, and you will have the linear distribution load, also called line load. The load is along a line, and so that is a several type. Concentrate force. Maybe the concentrate force hit the body, so it may have a concentrate force, and have the body force, and have the surface force, and have the linear force. Okay, whatever. So over a body, that is the pressure. The surface force may be like a pressure at one point. That is the concentrated force. Yeah, at one point, the external load at one point, that called concentrated force. Of if the actual if the force act on the narrow line is the linear distribution law, we call W function of S. Okay, we call it W. The W is the function of S. The S is the curvature on the body. Okay, the curvature or a line curve on the body. Okay, the Fr equal what? Fr equal the resonant force of Ws. The resonant force of Ws. That is very easy to calculate. You just integrate the Ws along this curve. That you got resonant force. Oh, you will get the resonant force of Ws. Okay, Fr equal the summation. You can the integration. Okay, the Fr equal the integration of the distribution load Ws along the S curve. Okay, and you have the body force. The body force, just like gravity, uh, or electric fields. Electric fields will cause the electric force. Okay, the magnetic fields will cause the magnetic force. Okay, and we have not only the external force. But also we have different support type. Okay, different support type. The support type is it's also very important to solve the problems. And in statics, maybe you will learn some called simple supporting condition. A simple supporting condition is just like a roller condition. Okay, roller condition, and maybe the subject is bounded by the cable. So in the end of the rod, you have the force act like this. You have the force act in this direction, and the direction is just like the table's direction. Okay, just like the table's direction. So you have only one unknown F, or on one unknown F. If there is a roller, we know the roller can support the vertical force, but it cannot defend the horizontal force. So if your body is a roller, if your boundary condition is a roller, you just have one unknown F. Okay, or if you have the smooth support is in this surface. The surface is smooth, so this rod can slide along this surface, but it won't jump out of the surface. So if it also have one unknown, and the support F is the normal direction of the surface. Okay, normal direction of the surface. That is important. And the general bearing, general bearing also just a ring, okay, ring constrain the body. Okay, ring to constrain the rod. Okay, but the rod still can move up up, force, back and forth, back and forward of this bearing, but it can jump. Okay, so you have only one unknown of F. Okay, that is the type of connection. Okay, another type of connection is the external pin. The body is pinned in this point, so it can, if it is a pin, the vertical and the horizontal force can both of the vertical and the horizontal force can be constrained. Okay, can be constrained. So in this point, you have the vertical force, vertical reaction force, and the horizontal reaction force. And if this is the internal pin, if you see the boundary is pinned, you should you should uh, you should think you should think it. Okay, it have the vertical and horizontal force. Okay, the internal pin, and if it is the fixed support. What is fixed support in this direction? in in this end of the body can allow any displacement, any movement, so it will have the vertical and the horizontal force to um, to pretend, or to not pretend, sorry, to to forces the displacement equal to zero, force the displacement equal to zero, and also it will have the moment to it have in this end, it have the external bending moment, not to um, to how to say, to balance, okay, to balance the force, to balance the external force causes the bending moment. So in this boundary condition, you have three unknown. One is f of x, f of y, and the bending moment. Okay, and the force being that it can allow this rod move move front and back. Oh, okay, move move forward, back and forward. Oh, sorry, it can, the forces bearing is won't allow the rod moving force and forward, back and forward. So it have two unknown, f of x and f of y. So you have to remember those type of connection that will causes the the when you calculate the internal force or internal stress. That is very important. The important point as you calculate. Okay. Okay. So we have noticed the external forces, the type of external forces, and we have also recognized the type of the connection. Those in different connection will causes different reaction, and the different reaction will causes the different internal force. The internal force will causes different stress. Okay, that is relation. Okay. Okay. So in real world, the cable, you can see in real world the cable example just like this, and the roller, okay, the roller and the smooth support, you will usually see in the bridge. In the bridge we have the roller support. This is the roller support. It support the bridge side, and this is the journal. The journal bearing. Okay, the journal bearing, like the 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 like this part. This part is the journal bearing. Okay. Okay. you will see this you will see this mm, this machine in the submarine, or in shapes, okay, in the shapes, okay, and okay, this is the journal bearing support, okay, journal bearing support. Let it have four unknown in 3D, three-dimensional problem. It have four unknown, okay, four unknown. And in one dimension problem, it just have one unknown. But in fact, in three-dimensional problem, it have four unknowns. That's we have to notice now. Okay, noticed. And in the chapter 1 to chapter in chapter 1 to chapter 8, we often discuss we usually discuss the one-dimensional problem. One-dimensional problem. Yeah. Okay. And in those condition, in the real world we have the pin. Okay, you see the pin condition, and in the basketball in a basketball field, you should see the fixed condition. Okay, fixed condition, and in this condition is very interesting. It have the fixed condition in here and the pin condition in here. It's very complicated, but still you can solve it if you have learned the statics well. So you can solve it problems, and this in the thrust bearing, okay, thrust bearing, okay. The thrust bearing condition is here. In three-dimensional problem, it will have five unknown, okay, five unknown. The Ry is there is one more unknown than the journal bearing. The difference is in the journal bearing. It don't have the Ry. Okay, you don't calculate Ry, but in the thrust bearing you have to calculate it. Okay, for some problem, the couple in both cases will be treated as zero to provide statistical determinants. Then we have to consider the equation of equivalent, That in the statics we usually consider the forces, okay, the external forces, the resonant forces, okay, and the summation of resonant forces, and we have to calculate reaction forces, right? Reaction forces in the pin side, in the joint side, in the fixed side. Okay, we have to consider the force balance. Okay, in those joint part. Okay, those connection part, but we don't calculate the forces. We don't calculate the forces inside the body. Okay, inside the body. So that is the difference in mechanical of material. So we have to consider the force inside the body. So the equation of equivalent. Now this is the body. I have four external forces, and if we have to consider the internal force, we should first select a plane. The plane will cut this body in two pieces. Okay. Now we focus on the lower part. Okay, the lower part. That is the external force is F1 and F2, and at this surface, the cutting surface, we say it is a cutting surface. Okay, the cutting surfaces have different direction of the cutting surface have a lot of particles. Yeah, and each particle have its own force. Okay, its own force. But we have to notice if this part is if this body won't move or won't have the if this body won't break or move or something else, just stay here. You just stay here. The body just stay here. That means low summation of the cut the cutting surface, the summation force of the cutting surface must balance with F1 and F2, right? Must balance with F1, F2. The summation of the force have the force balance with your external force, and the external force will also cause the bending moment, right? And the bending moment, since the subject won't move, so the bending moment also equal to zero. Won't move. It won't move forward or horizontal or vertical direction, and it won't flap. Okay, it won't flap. So if the body won't move or flap, that that means the summation of the force must balance with the for F1 and F2, and the summation of those forces causes bending moment must balance with F1 and F2. So the balance of force and momentum that told you summation F equal to 0 and summation M equal to 0 in 3 dimension f of x, f of y, and f of z that represent the forces in x direction, in y direction and z directions. So the forces can separate in 3 directions, right? Okay, x, y, z, and the momentum also. The momentum can be separate in 3 directions, mx, my, and mz. Okay, so the force balance told you the summation of f and the summation of the momentum, both of them equal to 0. Okay, in 2 dimensions, you have to calculate f of x and f of y equal to 0, and the mo is the certain of the body, okay, of the cutting surface, okay, certain of the body, okay. Okay, you can say the central, no, okay, central of the body, or central of the body. The center of the surface called O, so MO equal to 0. Okay, this is the 2-dimensional problem. Okay, now we have to calculate it. Okay. Okay, since in the central O we have F resonant force and the resonant momentum and MRO and FR, the resonant force FR and the resonant momentum MRO, yeah, in this point. So we could separate it into the horizontal direction and the vertical direction of this surface. Okay, the vertical direction of this surface also called the normal direction of this surface. The horizontal direction of this surface, we could say FR. If the FR separate in 2 directions, one is the normal separate in 2 directions. One is the normal direction and other is the horizontal direction. The normal direction force we call the normal force, and the horizontal force along this cutting surface we call the shear force. Okay, so the normal force we call N, the shear force we call V, and we know the magnitude of Fr is equal to square of N of is equal to the Fr, the Fr, the magnitude of Fr equal to N plus N Manipulate and add v manipulate v and squared result the squared result. Okay. Okay. And also the result of the momentum can be separated in two parts. And in the normal direction, it called the twistional moment, and the horizontal direction we call the bending moment. Okay, so the twisting moment and the bending moment and the Fr can be separated the normal force and the shear force. That called summation F equal to 0. The summation F equal to 0, that is summation F1 plus summation F2, the plus the shear force summation F1 summation F2 equal the normal force and the shear force. Okay, the sum and the momentum, the bending moment and twisting moment, that equal to the external force F1 F2 causes the bending moment and causes the moment at the all point. Okay. Okay. That is a coplane load. Oh, what is coplane load in this plane? Okay, and the different force. Okay, the different force act on the body, and that you can caught it in the same plane. In the same plane, that means the coplane loads, and can be obtained by applying Fy equal to 0. That is the coplane. That is the coplane. Okay, coplane load, and the MO can be determined by summation momentum about the point O. Okay, point O. Oh, summation MO equal to 0. That you have to consider. We have three. This is a three-dimensional problem. Okay, this is a three-dimensional problem. But if you can use it, that this x direction, y direction, and the outplane direction is z direction. And if you can put F1, F2, F3, F4 in the xy plane, there is no other force along the z plane that called the coplane load. Okay, coplane load. Okay, if you solve the coplane load, okay, you can see the F1 plus F2 equal what? Equal that N and V. Okay, equal N and V. Okay, so N can be obtained by applying F of Y equal to 0. Okay, F of Y equal to 0. Okay, so if we have to solve the equation of equivalent, we have to first we know the support reaction. The support is the pin support or roller or journal bearing or for whatever. Okay, so you have to know what support your body. Okay, and you have to draw the free body diagram. And the free body diagram we have learned in the statics how to draw it. You could just review your static textbook. You could know, okay, how to draw the free body diagram. Okay, free body diagram. Okay, to draw the free body diagram, you should do what? You should keep the external distribution load or moment or torque or force in their exact location. You have to check the exact location of the problem, okay, of the external load, okay, and draw the free body diagram. To draw the free body diagram is you select one section and cut it off. You have what? You have the normal force, you have the shear force, you have the bending moment. Okay, So the normal force and the shear force must balance with F1 and F2, and in the O direction you have to calculate the F1 and F2 in O direction, in the O point, what causes what moment. So you have another bending moment to balance it. So you have to calculate the normal force and shear force and the bending moment. Okay, at which point usually we select geometry center of, or we call central of the section area. Okay, central of section area. Of if the member is subject a coupling system of force, or coupling system of force, that is called coupling system of force, that is called, it won't have the what? It won't have, let's see, it won't have torque. It won't have the torsional moment. It won't have the torsional moment. That means t equal to 0. T equal to 0. That since the problem is coupling, so it won't cause as the torsional moment. Okay, it won't cause as a torsional moment. Okay, if you don't understand, I am willing to explain it in more detail in the office hour or the next time. But in this direction you have to know, yeah, the coupling loads won't have the torsional moment. Okay, won't have the torsional moment. So that means torsional moment equal to 0. Only normal force, shear force, and bending moment at the central. Okay, and you have to use. Usually we use the Cartesian coordinate. That means usually we calculate the equivalent equation. We use the x, y, z directions. Okay, so the final process is we have to calculate the equation of equivalent. Equation of equivalent, that is force balance, momentum balance. So, okay, this is the very simple example. That is a vein, and first we have to make sure that in A point it is fixed, and B it is free. So A have the forces boundary. The forces boundary will have f of x, f of y, and then we have a bending moment. Yeah. And the problem is to determine the resonant internal load acting on the cross section at C. Okay, cross section at C. Okay, and of the cantilever beam. So, and C, we have external load. An external load is like a triangle. It's triangle forces. Okay, triangle forces. At B, the external load equal to 0. At A, the external the load equal to 270. Okay, triangle. So now we have to calculate the moment. Okay, we have to calculate the normal force, shear force, and the bending moment at C. Okay, so we could choose this point, choose this section. Okay, choose this section, cut it off. We cut it in two parts. One is AC and one is BC. Both of them can be used to calculate the normal force, shear force, and momentum. But there is a more easy way to calculate the resonant force and resonant moment at C. Is we choose the free body BC. Why? If you choose the AC part, you have to calculate how much force at A, f of x equal to what, f of y equal to what, and the bending moment of A, and then you could calculate the result of C. And if you choose BC, we know in the free end there is no force at B, so what we should do, we just only calculate the resonant force, the resonant external linear force, or external force of the triangle force. Okay, the triangle force, and then we use the force balance and momentum balance. We could calculate the normal stress, the normal force, and the shear force and the bending moment at C. Okay, and then we should calculate this area. This area is represent the external force. Okay, the external force, and at C we could see that at A it is equal to 270. Okay, and at B it equals to 0. It's very easy to obtain at C. This external load is equal to 180. 180, and we have calculate this area. Okay, this area. Okay, this area is 180 plus 0 divided by 2 is 90, and the multiply 6 by 6. Okay, so the resonant force of the area of this triangle is equal to 540 540 Newton. Okay, and it will concentrate in the resonant force will locate at these triangles central. The triangle central. Okay, the triangle central is located. The ratio of the triangle central is 1 and 2. Okay, 1 and 2. So we could very easy to calculate it. The location of the resonant force. So the location of resonant force. The location of resonant force causes the bending moment is 540 multiplied by 2. So the bending moment, okay, the bending moment MC is equal to negative 1080. And since we have the force balance, V is opposite to the resonant force, so the VC equal to 540. Okay, so VC equal to 540. So there is no forces of NC, right? Okay, so NC equal to 0. It's very easy to calculate the result. And in the example 2, we could easily use this processing. Okay, we should the 500 engine is suspended from the cannonball in figure 1-5A. Okay, in this figure, and what you want us calculate? You want us calculate the internal loads action on the cross section of the bomb and point E, this point. Okay, so at this point we should draw the free body diagram of this body. Okay, which is first we could see in the AB A is the pin connection. Okay, so it have 2 unknown, and at C is a cable, which we can assume the C is the cable connection, so it have the only one unknown FCD. Okay, FCD, and we could have these free body diagrams, and first if we want to calculate the C, okay, the E, we have calculate the internal force at E point. We should first calculate the support force at A. Okay, at A. And support force at A is not very hard to obtain. You use the force balance and momentum balance. You can easily to obtain the FAX and AY and FCD. Yeah, use force balance and momentum balance. You can obtain the relation between AX, AY, and FCD. Okay, and after you obtain the AX, AY, X and AY, you could use the free body diagram. Okay, you could cut it off along the E point. Cut it off along the E point. Okay, along the E point, you have what? You have the normal force, you have the shear force, you have the momentum, and you have to do what? Do force balance and momentum balance, right? Oh, well, and the force balance and momentum balance and at the E point, okay, at the E point, okay, that you could calculate the vertical force and the normal force. The normal force balance told you NE is negative 9,810, negative 9,810 Newton, and VE plus AY must equal to 0, so you could calculate NE equal to negative AY. Okay, negative AY is negative 2.45 K Newton. Okay, and you could calculate the resultant momentum. The resultant momentum caused by the AY multiplied 1. Okay, multiplied 1. So ME equal to negative 2.45 kilo momentum. Kilonewton multiplied meter. Okay. And I will explain it in the Mandarin. Okay. 我们在算这个问题的时候，我们就比较快的去解释一下这个问题哈。就是说我们在算这些问题的时候，第一个最重要的就是找到你的这个力的这个支撑的形式哦。那如果支撑形式是 pin 的支撑方式的话呢，你就知道它会有2个未知数。那在 CD 这个地方呢，你可以知道说，在 CD 这边呢，可以像是一个 cable 的一个形式的支撑，好，所以你在这个问题上面呢，你就把这个还要算1点的这个内力，那你就把 AB 呢当成一个自由体图，把它取出来，好，那把它取出来了以后呢，你就可以怎么样？你就可以去计算了。第一个就是把 unknown 再写出来，哈，那你就3个 unknown。那这个时候呢，以 A 呢为支点，哈 ，A 为支点，那你知道什么呢？你知道引擎它的质量嘛，哈，那你不知道它的重量，重量呢就是质量再乘以重力，哦，9.81，所以你利用这个方式呢，在 x，在 x 呢做这个 f of x summation f of x 等于0 ，summation fy 等于0，还有这个 bending moment 这个等于0呢，那你就可以很轻易的去得到，好，你的 bending moment，好 fy。你如果以 A 为支点的话，这是更好的哈。A 为支点的话，这是更好的，因为 A 为支点的话呢，你就可以直接求出 FCD 了哈。A 为支点求出 FCD 哈，就只有这个嘛哈，分量这个分量不用嘛。FCD 乘以多少？3/5会等于什么 ？FCD 乘以3/5乘以2，好，这是它的 bending moment， 这是它对它的 bending moment 嘛。引擎对它的 bending moment 呢是500乘以9.81，好，再乘以3 ，OK， 所以你就可以很轻易的去算出你的 FCD 了。那 FCD 算出来了以后呢，你会有什么 force balance？force balance 呢 ，x 个方向跟 y 方向。x 方向呢就是 FCD， 好，就乘以4/5，然后就会等于 AX，OK， 所以你就算作 AX。那 FY 呢？FY 呢就是 FCD， 去乘以3/5，然后呢去减掉这个，然后呢 FCD 乘以3/5减掉这个加上这个哈，那你就可以算出来 AY 等于这个了。OK。那你算出 AY 以后呢，它算1的这个自由体图，对不对？1的这个体，你就从这边呢把它 cut off，OK， 把它切断，切断了以后呢，你就可以对1呢以1为中心点，1为终点去做什么？去做 force balance and momentum balance，OK，there is you can use it to do the force balance and momentum balance. That is easy to obtain the final result. The final result is just like as the previous we have to say force balance, moment balance，只是你现在支点换成是什么？你发现支点是换成是一这个点一这个点，那一这个点呢，对一这个点造成这个 momentum 呢就是 ay 嘛，对不对？ay，那你这个 m1 就是要跟 ay 去 balance，这个可能是比较难的地方。Okay, we have used two language to explain these questions. Okay, that means it's very important. So if you haven't learned very well of the statics, you should you should you should review it carefully, since we have do a lot of free body diagram, force balance, moment balance in this section. Yeah. Okay. And this is example 3. Example 3. And in the example 3, we have those trust. Okay, so just like a previous we have said, we just use the you could say you could see we have the line load and we have the concentrate load, so we have to see what he want, what what's the main point or what's the main target of these questions. The question is to calculate the internal force of the G. So you have to calculate the forces in the support point. Okay, you should calculate it first, and after you calculate the support point, that you can do what you can cut it off. Yeah, you can cut it off, and maybe you have to use the free body diagram of AG. Okay, of AG, right? It's very easy. If you have calculate it, you could calculate the force in the pin, the interaction joint. Okay, this point B. So you have to calculate the point B, and the point B will decide what? Decide the force AB. You have calculated the force AB, that you use the free body diagram of AG, that you could calculate the normal force and the normal stress, normal force and shear force and the bending moment at the point G. Okay, that is very easy to calculate the point G. If you use well, if you have a good if you learn well in statics, that is not very it is not quite hard to calculate those question. It's just like statics, or these those examples just to let you remember how to calculate the statics problems, how to draw the free body diagram. Okay, that is another, but this problem is a little bit different, since it is the three-dimensional problem. So it want to calculate for what? It want to calculate the section B, and you can see there was three external load. One is the vertical force and the horizontal force, and there is what? A twisting moment. So there is a twisting moment, and it wants you to calculate the internal loads acting on the cross section at B. So you have to consider this problem in three-dimensional questions. Maybe somebody will say, some of you will say, oh, that's very easy. We could calculate the force, okay, the force at C. So force at C on force balance and the moment balance at C, and we use the free body BC, so we could calculate the internal force at B. But if you consider more, if we consider furthermore, we do a furthermore consider, we will notice we'll notice there is something wrong. If we could calculate the point C, why we just calculate B directly? We could calculate B directly. That is very easy. Okay, so you could draw the free body diagram at B, but you could see it's very complicated. Have three forces and the three bending moment. In that maybe there is three forces at B and the two bending moment, one twisting moment at B. So there is six unknown. Okay, six unknown. So you have to use the three-dimensional force balance and momentum balance. But I think you could save it very you could save it very easily since you have passed the statics. Maybe I think you have to pass the statics. Okay, so you use the force balance and the momentum balance. Okay, you could calculate directly. Okay, okay, this is the and it want you to find out the magnitude of the force and the bending moment and the torsional moment. So you must to use the determine or the you have to use to calculate the magnitude of the forces, okay, or bending moment magnitude. Okay, then and okay, this is the part of reviewing the statics, and the next section or 1.3 section we have to we have to mention what is stress and what is stress and different direction stress, horizontal stress, normal stress, or causes different type of stress. Okay, that is the next time we have to say.